All right, welcome to part 2 of the midterm review for Weld 300. We are going to start this one off with gas metal arc welding. So gas metal arc welding is the second welding process that we get into in this course. It's, for some students, it's night and day from SMAW. So we're going to go over some of the similar topics that we did with SMAW. We're going to talk about power source. We're going to talk about polarity. We're going to talk about shielding gases. We're going to talk about electrode classification. All right, we got a whole bunch of stuff to talk about with each one of these topics: power source, polarity, shielding gas, and electrode classification. So the power source for gas metal arc welding is constant voltage. So if we think back to shielded metal arc welding, the power source for that process was constant current. And if we think back to why, when we are initially striking the arc, and after the welding arc stabilizes, we no longer need that high amount of voltage to sustain the arc. Eventually the machine balances out and focuses on just supplying a constant flow of amperage. Now, when we switch over to GMAW, we actually need a constant flow of voltage, and the reason for that is it's a semi-automatic process. So that means that something else aids us in the feeding of electrode into the weld. So literally we're pulling that trigger and it's feeding the electrode wire into the weld. And even though we can lengthen our stick out or shorten our stick out, that doesn't really change the size of our arc length. So by having a constant voltage, that allows for a more controlled or more regulated arc length. So even though we may increase our stick out or decrease our stick out, the arc length remains relatively the same. So just a little illustration of that. If we have our MIG gun, and here's our electrode wire, we'll give this one a relatively long stick out, and we'll have this MIG gun have somewhat of a shorter stick out. So if they're both just welding on a flat plate, the welding arc should be relatively the same length for both examples. So whether, again, longer stick out, shorter stick out, the arc length remains relatively the same because we have a constant flow of voltage. So when we think back to the volt ampere curve, where we have volts on this side, amps down here. So in SMAW, we would have a high open circuit voltage just to allow us to strike the arc. And then it drops down after the arc stabilizes and the machine focuses more on supplying a constant flow of amps. With GMAW, it's a little different. While we do still start with somewhat of a high open circuit voltage, it still drops, but not as much. There's still more of a constant flow of voltage in order to regulate the arc length. So just remember, with GMAW, we are using a constant voltage power source. Okay, now let's talk about polarity. So thinking back to when we first talked about polarities, we know that there's direct current and there's alternating current. And to break down direct current even further, there's direct current electrode positive and electrode negative. So using GMAW in our course, we are actually using direct current electrode positive. So the same polarity that we were using with SMAW. Now there are times where you could be using alternating current, but in our course, we are sticking to direct current electrode positive. So for all intents and purposes, if you see a question pop up regarding GMAW, just think back to this. We are using direct current electrode positive for everything we're doing in this course. Okay, now let's talk about electrode classification. So just like with SMAW, the electrodes that we use with GMAW also have a classification. They have a series of letters and numbers that are going to tell you a lot about the electrode. The particular electrode that we're using in our course is ER70S-6. And so we'll take this one part at a time, starting first with the letter E. So the letter E is following the same pattern as the electrodes from SMAW. So E stands for electrode. So upon seeing the letter E with any electrode, it's telling us that we can use this to start and basically carry a welding arc for the weld. Now we're going to see the letter R. This means that not only can we find this particular electrode as a wired electrode, but we can also find it as a filler rod. This will come into play in future welding processes where we can use the same wired electrode, but only as a filler rod, and something else is going to carry the current to create the welding arc, but more on that later. Now, the first two digits are going to be the minimum tensile strength. So this electrode, if welded in an appropriate manner, the correct way, these welds will hold up to 70 KSI, or 70,000 PSI, or pounds per square inch. Okay, and then the letter S stands for solid. So this means if we were to take a pair of wire cutters and cut the wired electrode, you'll see that it's solid all the way through. You'll find different welding electrodes out there. In place of the S, you could see something like a T. If you see something with a T, that means when you cut the wired electrode, you'll see that it's in fact tubular or hollow. There's going to be something in there. And you'll see some other electrodes out there with different letters in that place. But for now, just remember, if it's S, it's referring to solid, which leads us back to GMAW. And then the last number is going to be the chemical composition of the electrode. One thing that you're probably wondering about and notice that is missing is whether or not there is a letter or number that tells us what position we can use this electrode in. And so that is the cool thing about GMAW, is that all electrodes that are used with gas metal arc welding can be used in all positions. So it doesn't matter if it's flat, horizontal, vertical, or overhead, you can use the same electrodes for all of those positions. The only thing you have to change is your technique and the settings on the machine. So one more time, the E tells us that this is an electrode. So basically meaning we can use it to establish a welding arc and continue the welding arc throughout the duration of the weld. The R means that we can also find it as a filler rod. So something else is going to be creating and holding the welding arc, and then all we're doing is using the rod to fill in the weld. The first two digits are the minimum tensile strength. So again, if you weld correctly, then it'll take at minimum 70 KSI to break this weld. Now the letter S tells us that it's a solid wire electrode, and the -6 tells us where, or basically the chemical composition of the electrode. So again, I have this handout in the modules, so you can just find -6, go down the list, and you'll be able to view what the chemical composition is. All right, so next up, let's talk about shielding gas. Rewinding back to SMAW really quick. The flux coating on the electrodes provides the shielding gas as it burns off. Now the electrodes that we use with GMAW do not have a flux coating. So that means we need to have our shielding gas provided by some other auxiliary source. And so that's where we have cylinders with compressed shielding gases. Now there are a few different shielding gases that we can use with GMAW. One of them that we'll talk about is argon. And another one that we're going to be talking about is CO2. Now before I get too far into that, I want to take this time to point out that GMAW was once called MIG, or metal inert gas welding. And so the reason for that is because initially we were only using inert gases to protect the weld. And so inert means that the shielding gases do not chemically react with the weld. And argon is an inert gas, which means that when we use this as a shielding gas, it does not chemically react with the weld. On the other hand, CO2 is not an inert gas, which means that when we use CO2, it does chemically react with the weld. So that is why we call it gas metal arc welding instead of metal inert gas welding, because now we've opened up this welding process to much more than just inert welding gases. So let's start off with argon. Let's first remember that it is an inert gas, so it does not chemically react with the weld. It's also fairly inexpensive. So when we think about producing argon, think about the elements that are in the very air that we breathe. So when manufacturers of compressed gases start separating the elements in the very air that we're breathing, when they isolate oxygen, pretty much what's left over is argon and trace amounts of every other gas that's out there. So it's relatively easy to manufacture and produce cylinders of argon because it's a byproduct of capturing 100% oxygen and then packing that into a cylinder. Another thing about argon is and I won't go too deep into it, this will get covered in other classes, but a lot of the characteristics of argon allow for a much more controlled and stable arc. So we'll say more stable arc, or more of a stable arc. And this is going to help us to go from short circuit into spray. Now, there are times where we use argon by itself in a 100% mix. So that's for certain metals like aluminum. However, one thing that you should remember is that in this class, we're welding carbon steel. So we're not actually using 100% argon. We're using it in a combination or a mixture with some other type of gas. And that gas is CO2. Now remember, CO2 is not inert. There are some upsides to using CO2 though. The way that CO2 interacts with the welding arc, not to say that it's unstable or erratic, but it's not as stable as when we just use argon. So using CO2 does allow for a much hotter welding arc. Now, depending on our technique, this will allow us to achieve greater penetration. The one thing that I will say about using 100% CO2 is that the amount of spatter that is going to be produced is going to be a lot more than by adding argon. So CO2 by itself, you're going to see a lot more spatter. By introducing argon into the mix, we can actually cut or reduce the amount of spatter. And the same thing, CO2 is relatively inexpensive to produce because it's in the very air that we breathe. Now there are times where you'll use CO2 just by itself. It's a gas that again is very inexpensive, so a lot of places will actually use this gas while they're teaching welders, students how to weld. It's inexpensive, don't have to worry about running through a whole bunch of it, but here we don't use CO2 by itself, nor do we use argon by itself for this course. We're actually using an 85-15 mixture. So that is 85% argon, 15% CO2. Now, some places will actually say that a better ratio or a better mixture would be 75% argon and 25% CO2. But it really comes down to what work you're trying to do. Because our program does incorporate spray mode in later courses, and you'll find all this out later on, but it's actually advantageous to have a higher presence of argon. That way achieving spray mode is actually it's easier. So you need more argon in order to successfully get past globular and into spray mode. So that's why we don't have any 75-25 mixes. We just use 85-15 just to keep it plain and simple. All right, next up we have modes of transfer. Now under modes of transfer we have short circuit, we have globular, and we have spray mode. Now we can take spray mode one step further because there's also something called pulse spray. But This is something that you'll focus on more in later classes. For now, just know that there are basically 3 modes of transfer when it comes to GMAW. So, short circuit. Short circuit mode utilizes a lower range of voltage and wire feed speed. What this means is that when we're using short circuit, we're not getting as much penetration as we could using the other modes of transfer. Not to say that you're not getting any penetration at all, you're just not getting as much as might be ideal for the work that you're doing. So basically how short circuit works, if we have our MIG gun, and here's our plate, your wire is going to feed through until it makes contact with the base material. Once it makes contact, it's going to complete the circuit, and it's going to allow for current to go through, and it's actually going to heat the electrode up just a little bit to where some of it melts off, and you'll see an arc. And once that happens, the arc kind of cuts out shortly after. The electrode comes back out, makes contact again, all right, and then it heats up, melts, an arc is established, and the electrode that melted off becomes part of the weld. Now this happens hundreds of times a second, depending on the settings. So this is the reason why it's called short circuiting, because essentially every single time the electrode hits the base metal, it short circuits essentially. So a bit of it pinches off, the arc, an arc is created, and that allows the piece of electrode to melt into the base metal. All right, now let's talk about globular. So globular is kind of similar. So we still have a MIG gun. We got our electrode, we've got our base metal. Now, when the electrode touches down, makes contact, same thing. There is some resistance going on because of the closed circuit. Now, when the electrode heats up and melts off, the arc is established, but instead of the electrode then pushing past the arc after it cuts out, making contact again, what happens is the electrode gets pretty heated, and we have bits or sections of the electrode that melt and gather into this glob, this molten glob, and it accumulates at the very tip of the electrode until the globs essentially get too big or too heavy and separate from the electrode and then fall across the welding arc and become part of the weld. So it's called globular essentially because globs of electrode are melting off and becoming part of the weld. Now this creates for some things that are unideal. So excessive spatter, because we can't control how the globs form and travel across the arc. When they make contact with the weld, sometimes it's just too much metal and some of it splashes out and becomes spatter. Now we have spray mode. So just like with the previous two, we have our MIG gun, we've got our electrode, and we've got our base metal. So pretty much the same thing. Our electrode is going to make contact with the base material, and an arc is going to establish. But now, instead of, like short circuit where the arc eventually cuts out and the electrode makes contact with the base material again, or instead of like with globular where a bunch of metal accumulates at the tip and eventually when it's heavy enough it just breaks apart, what we have instead is as the electrode reaches, or as the electrode, basically reaches the arc, it melts off and becomes little droplets of molten metal. And so that allows us a much more controlled deposit of metal into the weld. So a lot of places out in industry will use spray mode because it's at the higher end or the higher ranges of volts and wire feed speed. So we can get better penetration using spray over globular and short circuit. Okay, now let's talk about metallurgy. So when we think about metallurgy, we're thinking about the changes to the physical and mechanical properties of the metal that we're working with. Now, pretty much everything has a grain structure. Wood has a grain structure, plastic has a grain structure, ice has a grain structure, steel has a grain structure. Now, we are going to be talking about a few different properties, or we're going to be talking about a few different topics. So, kind of leading off with grain structure, we're going to be talking about crystalline structures. That's just a fancy way of saying grain structure. We're going to talk about mechanical properties. All right, we're also going to be talking about the various types of heat treatment. And we're also going to be talking about carbon content. All right, so let's talk about the crystal structures. Remember, this is just another way of saying grain structure. So if we were to break a piece of steel apart and basically look at the cross section under a microscope, we would see grain structures. We'd be able to see iron and carbon, coming together in different formations to create the grain structure. And at its very basic form, steel is made up of iron and carbon. Those two elements come together to create steel. Now, when we start talking about crystal structures, think of everything as a cube. So let me get a cube going for us. And forgive my drawing if it doesn't come out too good. Okay, so we have our basic cube. Now, this is what we're going to be covering is called body-centered cubic. So this is the formation of those grain structures when steel is at room temperature. So what that means is that pretty much in the corners, there's going to be an iron atom. And there's going to be some on the other side, some behind here. We just can't see them just yet. And every so often, there's going to be a carbon atom. Not to say that there's three, but this is just kind of showing you that in between the iron atoms, there is some carbon. Now, stepping away from steel for a moment, think of things like ice or water. When it heats up, it expands. And everything pretty much as it heats up, it's going to expand. Now, things do eventually catch fire and burn, but just before it gets to that point, it's going to expand a little bit. Steel is no different. As we heat steel up, it's going to expand. This is where we see a transformation of these grain structures go from body-centered cubic to what's called face-centered cubic. Okay, so the shape of the cube does not change. We still have a cube. Okay, the only thing that changes is that now, instead of iron being restricted to just the body of this crystal structure, we now find iron. On each face. So in addition to the iron around the body, there's going to be an additional iron atom on each face. So this iron is essentially kind of expanding, stretching out, and sorry, these drawings aren't exactly to scale, but when steel expands, it allows for more carbon to enter in these spaces between the iron atoms. So we have more carbon entering the mix. Now this is as heat is applied. Once the steel reaches what's called the transformation temperature, it no longer has its magnetic properties. So think of when metal reaches kind of like an orange glow. All right, it's no longer magnetic. So face-centered cubic, non-magnetic, transformation temperature, or just very hot. You have expanded grain structures, extra carbon finding its way in, versus body-centered cubic, which is something you would find at room temperature. Somewhat of a smaller grain structure, not as much carbon in between the bonds of iron. Now, how this plays a role in welding is when we get to heat treatments. But for now, just remember this. Body-centered cubic, room temperature, you have iron atoms around the body, and you have some carbon atoms floating around in there. As you apply heat, this crystal structure moves from body-centered cubic to face-centered cubic, where now we have additional iron atoms on the face, and it allows for more room for additional carbon atoms to just float their way in, essentially. Okay, now let's move on to mechanical properties. There are 4 mechanical properties that I really want to stress on. The first is hardness. The second one is brittleness. The third one is ductility. And the fourth one is strength. So hardness is essentially the characteristic that allows steel to resist penetration or puncturing. So we'll say resistance to penetration. Actually, I should have said surface penetration. So think of using a hammer and chisel or a center punch, or if you wanted to simply scratch the surface of steel. Depending on how hard it is, it's going to be harder or easier to penetrate the surface of steel. Now, brittleness is how easy the metal will crack or break when you try to bend it. So we'll say for brittleness, it is the ease which steel cracks or breaks. Ductility is essentially the ability of steel to be bent, twisted, basically have its shape changed without cracking or breaking. So we'll say ability of steel to be bent without breaking. And strength is the ability of steel to resist being bent or twisted out of shape. So we'll say resistance of steel to be bent or twisted. Now, all of these do kind of overlap on one another. It is virtually impossible to have steel that is very hard, think extremely hard, while also maintaining an ideal level of ductility. You cannot have both. It's one or the other, or you find a happy medium. So as hardness goes up, so does brittleness. Ductility will go down. If you have something that is very ductile, it's not going to be very hard. So there's a lot of these where if you start changing one property, you start changing others. And so in order to achieve an ideal amount of either one of these properties, you have to cycle the steel through being heated and cooled off at certain rates. Basically, you have to heat treat the steel depending on how you want that steel to have these four properties. All right, let's talk about heat treatments now. Heat treatments can sometimes be a little confusing. Actually, to kind of sidetrack from the review for a little bit, if you've ever watched Forged in Fire, it's a great show that showcases varying degrees of heat treating. So the first one we're going to be talking about is hardening. We're also going to be talking about tempering. We're going to be talking about normalizing. And we're going to be talking about annealing. there's a more extensive list of heat treatments, but for this course, these are going to be the 4 that we focus on. So let's talk about hardening. So when we harden something, we are essentially increasing its hardness, just like the name implies. Okay. We're also increasing strength. But we are decreasing ductility. And by decreasing ductility, that means we are increasing brittleness. So an easy way to explain hardening is think about what you do in class. You're welding, and before you bring it up to me to be graded, what do? You cool it off. Now, some of you let it cool off under a fan or by itself, and a lot of you use a quench tank. So when you think of hardening, think of quenching. So some people will refer to this as quench hardening, where you superheat your metal and then you dunk it in something to rapidly cool it off. So when we talk about heating it up, we're heating it up to the transformation temperature. And then rapidly cool it off. Most times this is by dunking it in water. Some people dunk stuff in oil and sand, whatever. But in our class, we're quenching our steel in water. All right, next up, let's talk about tempering. So tempering is where we're taking something that is already hardened and we're softening it up a little bit. Not to the point where it's as soft as its original state, but we're softening it just enough to decrease brittleness and increase ductility. So how we do this is we heat the metal up below the transformation temperature. And then once we heat it up to its once we heat it up below the transformation temperature, we allow it to cool off by itself. So this means we're not setting it in front of a fan that's pumping out air or cold air. We're not dunking it in the water. We're not setting it in sand. We're allowing it to cool off by itself. So what this does is it decreases brittleness, it slightly decreases hardness, only to the point where you're increasing strength and ductility, but mainly ductility. Think of our tools, think of chisels, think of our kitchen knives. So you want something that's not gonna break, but if you're cutting something that's really thick or really hard to cut through, sometimes we might end up bending our knives, and our knives are actually tempered if they're made out of 100% carbon steel, to the point where if they do bend a little bit, they're not just going to break or crack or shatter. All right, now let's talk about normalizing. So normalizing can be done to metal that's either hardened or tempered. The purpose of normalizing is to get rid of as much internal stress as possible, or basically return the steel to its original state. So we're taking something that's either hardened or tempered and bringing it back to its original state, or as close as we can to its original state. So this would be getting rid of hardness and brittleness and bringing back ductility and strength. So this happens by heating it up, or heating the steel up to the transformation temperature. Once you get it up to the transformation temperature, again, just like with tempering, you're going to allow it to cool off by itself. And the last heat treatment we'll talk about is annealing. So this is where we take steel and we bring it to its most ductile state. We can do this with anything that's been hardened, anything that's been tempered. We can even do this with metal that's been normalized. What we're doing is we are increasing ductility as much as possible. We are essentially softening the steel. So how we do this is we heat the metal up to its transformation temperature. And we do what's called a soak. So a soak means we keep applying heat. So once we get it to its transformation temperature, we keep applying heat, not to the point where we're going past it, but just to the point where we're maintaining that high temperature. So we're going to hold it there for a certain amount of time, and then we are going to slow cool it. Slow cooling rate. So it's not the same as just letting it cool off by itself. What we're doing by decreasing the rate of cooling is actually taking away a little bit of heat over a prolonged period of time to really drag out that cooling time. So depending on the temperature, maybe an hour goes by and we reduce the temperature by 100 degrees. The next hour we drop it by another 100. Whatever it happens to be, depending on what you're trying to achieve, where you're working, the type of work you're doing, you're just heating it up to its transformation temperature. You're holding it at that temperature for a certain amount of time, and then you're slowly decreasing the heat, again, over time, until it is about room temperature. And this is to soften the material as much as possible. So when we talk about transformation temperature, I'm sure you're all wondering what exactly is the transformation temperature for the steel that we're using. Now this gets a little tricky because transformation temperature is actually based on carbon content. So the carbon content is going to dictate the transformation temperature. There is a lower transformation temperature and there is an upper transformation temperature. The lower transformation temperature is approximately 1,333 degrees Fahrenheit, and the upper transformation temperature is approximately, 1,670 degrees Fahrenheit. So depending on the carbon content of the steel that you're working with, Your transformation temperature could be here, it could be somewhere in the middle, or it could be all the way over here. And that leads us to carbon content. So in regards to carbon content, there are three types of steel that we'll be dealing with. There's low carbon, there's medium carbon, and there's high carbon. Now, each different type of steel has its own different uses. Some are used in everyday household application. Some are used in fasteners like screws, nuts and bolts. And some are used in more like tool steel, drill bits, wrenches, chisels, and you can even think of like knives, vehicle frames. Every category of steel is used somewhere in life. And I won't get into that too far. I'm just going to explain the carbon content range for each one of these three types of steel. So low carbon steel has a carbon content anywhere from 0.05% all the way to 0.3%. Medium carbon steel contains anywhere from 0.3% to 0.6%. And high carbon steel contains anywhere from 0.6% all the way to 1%. So as you can see, there's not a whole lot of carbon in steel. Now, it doesn't take a whole lot of carbon to change the mechanical properties of steel, bringing it from low carbon to medium or to high, or just the reverse, taking it from high to medium to low. Carbon content is also going to, as we established before, it's going to dictate your transformation temperature, and it's also going to dictate the level of hardness, brittleness, ductility, and strength as you cycle it through the various types of heat treatment.